Approximately a year ago, I featured a flickering effect flame simulation lamp, and I was really impressed at the time. A company had actually approached me. I didn't even know they were available in the market. They approached me and asked if I'd like one as a sample to do a sort of video on. And I said, yeah, that looks really interesting, and they duly sent one out. But obviously they hadn't looked at my channel beforehand to see what I do, because I completely took it to bits and reverse engineered it, and they went ape shit. They went absolutely nuts, and they made me take the video down. And at the point I'd put the video up, their website got so many hits that it got actually taken down by the demand. And then, as soon as the video was taken down, they then suddenly realised that all these advertising hits weren't coming into their website, they weren't making any sales. And they said, well, you can put the video up again in a censored form. And I did, and then they started messing around. Then I just thought, screw that, and I took it down. And then they said, oh, okay, you can put it up in its original form. So now, 1 year later, the market is just absolutely covered in. It was so predictable that it was such a nice effect that people were going to copy these left, right, and centre. So I thought it'd be worth getting one to see what it looks like inside. And this one, the visual effect of this one has improved greatly. The pattern of the original one was quite a simple pattern. It just went in a very short loop. You could see the point it looped. This one does have a recurring loop in it, but then it steps onto another pattern. It's got a recurring loop, then another pattern, recurring loop. And all in all, it's very good. Also, as other people have mentioned with these things, it's got that extra feature that sometimes the flame licks up and it leaves the other LEDs completely, and that's quite a good effect as well. So it's quite a nice visual effect. It's being swamped about a bit in camera here. I've set the camera for one exposure because I'm going to be showing lots of, well, the schematics for this really, basically. So I've set it at a level that, you know, they're going to be bright, and it means this is just that little bit over swamped as it is. So if I open this up, tell you what, before I start this, many eBay listings, this thing is really common. I think this is the one I got this one from, because I ordered a few of a recent style. And the typical keywords are things like burning LED light, flicker flame lamp, and it's just basically flame lamp really does this sort of job for bringing these up. There's an awful lot of them, a lot of new styles, and quite a wide price range too. This one is shown as £2.99. It wasn't. It was £6.99. I wouldn't expect them to be much cheaper than that at the moment because they're quite complicated inside. I shall crack this one open and you'll see. I'll crack open the power arm, which is probably ill-advised. And inside is the same arrangement the original had, which is this round. I've checked this so I know I'm not going to get a wallop off this. It's got this round sort of circuit board with what you might call a video wall of LEDs on it. A circuit board, an active circuit board in the bottom, and then it's got a power supply section in the base. So the power consumption of this, it does that thing again, that if you turn it off and on again quickly, it comes on and it goes into another mode. It's a bit unpredictable. There it is in the ramping mode. The other mode was the fixed mode, and then it should be back round to flicker flame mode again if you just sort of turn it on and off at the switch. But by default, if you turn the switch off for a while and then power it back up once the little capacitor inside is discharged, then it will automatically start in the desired flickering mode, which is the main mode. That's what you want. Power consumption at full output, if you put it full on, is about 3 watts. I've just suddenly forgotten what the power consumptions are. Let me grab the hoppy and we'll check this out. So let's bring the meter in. We'll plug this in here. Plug this into the hoppy. Plug the hoppy in. And it prefers some real flicker from the hoppy display. It's showing the power roughly about 1.6 watts. Power factor is terrible. It's what you'd expect from a very simple switch mode power supply. It's not really that relevant. Given the power consumption is so low in the first place, it's showing about 16 milliamps. If I do the sort of off and on again to bring it up to full intensity, it's just not worked. Let's try that again. Oh, no, I know what that is. That's the plug popping out. That's what's happened there. Because of the hoppy meter's slight weakness and the sort of the terminals underneath that block these plugs. At full power, it's showing about 3.9 watts. And about 36 milliamps. So at full power, it's actually quite bright. And at the dimming mode, I've never really twigged out why they'd want this dimming mode. It just basically ramps up and down. But the flicker mode is the main thing of interest. It's about 1.6, 1.7 watts, but it bounces up and down because as the pattern changes, the current goes up and down a wee bit. Okay, we've ascertained those details. Let's take it to bits. Well, I've already taken it to bits, but let's explore it a wee bit further. So, as before, it's got 3 sections of LEDs around here, and they're all made up of what you might call diagonal pixels to give it a sort of non-blocky look. And the arrangement of the pixels is like this. So there are 3 sections like this with, how many LEDs are there? I'm trying to remember now. 1, 2, 3, 4, 5, 10, 20, 30, 33 LEDs in each section. So it's got about 99 LEDs total. Because this is repeated the 3 times around the side. So it goes round to about here, then repeats from about here onwards, and it is just a emulation again. And initially I thought, well, that means, given how many channels there are, it's like effectively 5, 10, 15, 16 channels. I thought maybe the little microcontroller just has 1 pin per output, because there's lots of transistors. There's literally 1 transistor per sort of circuit, but it's not like that, and that's because the microcontroller inside only has 14 pins, and they do something really quite clever. So I'll just put this out the way at the moment and bring in a picture down the end of that, because you're not going to really be able to see much in the dark here. So if you look down the end, there's the microcontroller, and it's not got markings on it. The transistors all around it appear, most of them are marked A2SHB. The A2 is a fairly generic N-channel MOSFET. The ones I'm not sure about are these 2 down here, because they have a different function. However, I've got the feeling they're just the same thing. So before we go too deep into this, let's get the power supply out of the way. The power supply, this will look a bit out of focus because I focused down onto the circuit board itself. We've got the mains come in, going through a bridge rectifier. There's a smoothing capacitor here, and then 1 universal, 1 chip does all. It's an AT chip, ATC9501. If you look that up online, you'll find not much in the way of data sheets other than the datasheet archive type companies pretending they've got the PDFs. But it's a very common chip by AT chip, and it's used for making very simple, usually 5 volt switch mode power supplies. And the output of this power supply from this transformer here is the rectifying diode, a small loading and discharge resistor, and then the capacitor, and then the 2 tails coming off and going to the circuitry. It's got this foam pad stuck on top. It's much lower profile than that. The foam pad is merely just to stuff this down into the base when the rest of the lighting module is put in, just to stop it rattling about really and keep everything in place. Very, very simple. This is 5 volt output. That's important because that means that this module can be run off a USB power supply, or it can be run off a power bank. And at the end of this video, I'm going to connect a couple of leads and we'll see if it runs off this little power bank, because that would make it great for props, theatre props, just parade props, or just whatever you wanted. You could basically have a flame the top of your head if you wanted some fancy dress. You could use gasoline for that too, but it's not really recommended. So the power supply out of the way, it's a very standard power supply. Let's bring in the 2 bits that are interesting, the front and back of the circuit board. To help reverse engineer this, I did have a flipped version as well of the top of the circuit board, should I say the underside of the circuit board, because although all the text is back to front in this, it makes it much easier to sort of correlate pads and tracks and plated through holes where they go through the circuit board. But these ones are sharper and clearer. So the 5 volt comes on, and the first thing that happens is there's 2 little capacitors filtering here, but in reality there's another little capacitor here. It's very odd how they've done that. But they've effectively got 3 local capacitors for decoupling. I thought one of them was for detecting the power going off and on again. I think it may have, to a degree, that function as well, to tell it to go into the next mode. But it's not obvious how they're doing that. I think it is a little bit of trickery inside this chip. The chip only uses 1, 2, 3, 4, 5, 6, 7, 8 lines to actually drive 16 transistors. And there's another 2 transistors switched by these 2 lines that switch them in banks. Let me elaborate on this by showing you a little doodle I did earlier on. I've never seen this before. It's a very odd way of multiplexing. So basically speaking, here's a CPU, and it can turn on bank A via this MOSFET, or it can turn on bank B. And all it does is that then creates a negative rail with the 8 MOSFETs on that rail sitting on top of that. So they're basically 2 MOSFETs in series, which is odd. I've never seen that before in that particular style. The CPU has the 8 output lines, and it's got one resistor, a 1K resistor, but it feeds the gate of both MOSFETs in bank A or B, but only the one that's actually effectively able to reference to ground via the 0 volt rail via its main switching MOSFET will be the one that lights. So effectively, it means they only need the 8 output pins plus the 2 bank pins to actually allow driving of the full 16 channels. Each transistor, of which there are 8 on each side, it really is just covered in transistors, has an 11 ohm resistor, and then it connects to the LED panel by 1 pin. But on that panel are 3 pairs of LEDs. In the case of the top one with 3 clusters, the 3 LEDs at the tip of the flame, it's got 9 LEDs on that particular channel, but they'll ultimately use the same current as all the others just because it's one resistor feeding them. That's a very odd arrangement. And that is fundamentally, if you can imagine this bit of the circuit repeated 8 times that side, and that bit repeated 8 times that side, that's fundamentally it. Other things worthy of note. So those 8 pins, which is one nice round byte in microcontroller terms, are driving the 2 banks of transistors via these little resistors here. And literally, in the case of this pin, it's connected to the 1K resistor, 102, where the 2 means 2 zeros, 1000, 1K. So that connects to that transistor, but then it also skips over to the other side, and it connects to another transistor in the matching bank. It really is just that simple. The power rail here has a negative going to this pin at this far end of the chip, and the positive going to this pin at this end of the chip. But this pin here, it's a 14-pin chip, pin 13, is also connected to the negative rail by a 0 ohm link, which I'm not sure if that's part of the circuitry to detect the power up, because the only other pin that's available is this pin here, and that one is connected via, I think it's a 10K resistor, to the positive rail. I thought it might have been connected to, it's connected effectively to this, but this, I thought this was going to be some sort of little timing circuit that when it was powered off, in the time it took this to discharge, it would then, if it was powered on again before the voltage had gone down that, it would detect that, it had been turned off and on again quickly for the mode change. But it doesn't look like that. This capacitor here is effectively in parallel with these ones via a convoluted track. And then this resistor just going to that pin from that. I'm not sure. It might even be a PIC microcontroller. That might be the master clear pin that is a common practice to use a 10K resistor to pull that high. Not sure. And that would then make this pin suspicious as possibly being monitoring the power rail in some way. Or it could be inside. I'm not really sure how they're detecting it being turned off and on. But after that, that's fundamentally it. I mean, it took a long time to actually reverse engineer this because there's a lot of circuitry and it's very, very small, and it wasn't overly clear what was happening initially because I was thinking, how's it driving so many transistors with so few pins on the microcontroller? And that's what it was, just these 2 big bank switching transistors down here, and then all the smaller transistors, and that's fundamentally it. It's a very good effect. Anyway, let's convert this to USB operation by bringing in a pre-prepared fetching pink USB lead. And I'll start by whipping these leads off the bottom of the lamp. This just opens up so many possibilities for special effects and stuff like that. It also means it's a lot safer and more convenient for, well, particularly, if you're going to be walking about, you don't want a 240 volt or 120 volt one. I'm guessing this is a universal power supply. Not sure. Does it say in the case what it is? No, it doesn't. No, it doesn't say anything. So I'm going to flow a bit of extra solder onto those. Make sure I get the polarity right. That would be a disaster if I didn't. I've already checked the polarity of this lead, that it's correct. So let's So the positive on. And the negative. And at this point, I should be able to, well, I'll turn the power supply off for the soldering iron so it stops making noises. I should be able to just plug it into this USB power supply. And there we have a USB power supply powered flickering flame. It's a good effect. It's a very good effect. It's one of the better ones. The only weird thing is it does a lot of shimmering at the bottom, but that's strictly in the software. I suppose that are just wanting a bright base at the bottom to emulate the sort of flickering lamp, and then these bits of the flickering, the taller flames just licking off that. It's very good. They have really evolved. I'll just cup my hands around it like this so you can see the sort of effect. And of course, depending on the sort of angle you view it, you'll see other elements of that as well. It's very good. Can I tell the power that's running off this in the USB? Where's my little USB power monitor thing? I take it if I unplug this and plug it in quickly, it will go into the other modes. Oh, it's not. Oh, that's because it's not got the big smoothing capacitor here to actually rely on. Okay, that's actually quite good in a way. So because it's relying on the tiny capacitors on board, the voltage is dropping instantly. So most time it's just going to go into straight flickering mode. And the power consumption, it's trying to analyse the power consumption. It's saying roughly 180 milliamps on average. Peaks about the 220 milliamp mark. That's all right. That's going to give you a very long runtime off a USB power bank. Now, another thing I did with this, I just hot-wired. I got some leads and I put them straight on across the capacitor and the output, the power supply, but left the power supply off. And I tested it, and the voltage it kicked in at, anything less than about 3.6 volts, it just flicked. As soon as I exceeded about 3.6 volts, it lit, and the current it drew when it was at the sort of stable operation of about just above 3.6 was 100 milliamps, and it was still very good and visual. Obviously up at 5 volts it's 220 or so milliamps, but that means that it is suitable for battery operation. You could get a set of 3 nickel metal hydride cells maybe. I'm not so sure about the using a lithium cell because the voltage could go down quite, but by the point it's reached about 3.6 and this goes unstable, it's kind of, that's the battery sort of half depleted, perhaps. But having said that, that's all a moot point. If you get the USB power bank, it means you can run this for a good long time. And if you got a big chunky power bank, I would reckon this would run that for a very long time indeed. I've never tried that. I wonder how long it would run on a fully charged unit. I suppose a good indication would be to put a known lithium cell in there of a known value and just see how long it ran before it cut out, and then you could multiply that by the amp hour rating of the lithium cells inside. But yeah, it's a very good effect. I like it a lot.